Hello students, a warm welcome to all of you. Today we are going to start with the last and the final topic of the entire syllabus of signals and systems, that is realization. Now what is the meaning of the word realization of filters? As of now, we have seen the development of filter. Like example, we have seen Butterworth low pass filter, Butterworth high pass, band reject. We have seen Chebyshev low pass, Chebyshev band reject, and so on. Now, after studying the transfer function, the amplitude response, filter is going to behave. After understanding all this, now question to arise, like how to develop, how to realize these filters on breadboard, because we being the electronic students, how can we use this filter for the development, for the implementation on the hardware? So for that we are going to understand today is the realization of filters. Now before we start, I'll share the screen so that you get more understanding for your perusal, like how these things have to be done in more better way. That if you look in the syllabus 5.3 realization diagram, wherein we have form 1 and form 2. For that, I have shared with you first is there are four types of realization: direct form 1, direct form 2, cascade, and parallel realization. As far as syllabus is concerned, we're only restricted with direct form 1 and direct form 2. Now you're going to start with direct form 1 realization. Any filter, any system can be represented in the form of mathematical expression. So consider I have an expression like d cube by dt cube y of t minus of 3 by 8 d square by dt square y of t minus 3 by 32 d by dt y of t minus of 1 upon 64 y of t equal to 3 d cube by dt square x of t plus 2 d square by dt square x of t. Now if you try to figure out in the expression that we have y of t, y of t, y of t, y of t on the left hand side, and we have x of t and x of t in the right hand side. As you have rightly predicted that y of t corresponds to output and x of t corresponds to input. Now I'll be converting the entire given differential equation representing the relationship between input and output in the Laplacian domain, which says differentiation in time domain is simply a multiplication by s in Laplacian domain. So since I'm having here as d cube, so I'll be calling it as s cube. So I have s cube y of s minus 3 by 8 s square y of s minus 3 by 32 s y of s and minus 164 of y by s equal to 3 by 3 of s cube x of s to s square x of s. Now I'll be keeping s cube y of s on the left half, and remaining all terms in the left side will be transferred to right hand side, and eventually I will get 3s cube x of s plus 2s cube x of s plus 3 by 8 s square y of s plus 3 by 32 s of s plus 1 upon 64 y of s. Dividing the entire expression by s cube so that y of s will be coefficient free. So I get y of s equal to 3x of s plus 2x of s plus 3 by 8 x y of s upon s plus 3 upon 32 y of s upon s square plus 1 upon 64 y of s upon s cube. And then what I'll be doing it is like entire expression I'll be writing in the SFG form, signal flow graph format, wherein I can say y of s, the output is y of s, output is y of s. So y of s is equal to x of s multiplied by 3. So x of s, I will draw an amplifier block with a gain of 3 and 2x of s. So I have here again an amplifier block of 2, amplifier block with the gain 2, and S, so 1 upon S, 1 upon S, 1 upon S as the gain of that loop, so 1 upon S 2 in addition form plus, and then I have here as 3 by 8 1 upon S, 3 by 8 1 upon S, 3 upon 32 1 upon S square, so 3 upon 32 1 upon S square, so 1 upon S multiplied 1 upon S will give me 1 upon S square, and lastly what we have is 1 upon 64 as the amplifier, 1 upon 64 as the amplifier, and 1 upon S again 1 upon S cube, so I have here 1 upon S 1 upon S 1 upon S gives me 1 upon S cube, and this again I put in this loop. So now I can have y of S is given as 3 of x of s plus 1 upon s multiplied by 2 x of s, and lastly we have 3 by 8 of y of s, 3 by 32 y of s, 1 by 64 y of s with 1 upon s, 1 upon s square and 1 upon s cube, and this is what we call it as df1 or direct form 1 of the given differential equation in time domain. I hope you have understood how df1 has to be drawn, how df1 has to be plotted. Now we move towards direct form 2. If you talk about direct form 2, first and foremost, as per the examiner, this will be the differential equation given in front of us, which goes like d square by dt square y of t plus 0.6 d by dt y of t plus 0.7 y of t equal to d square by dt square x of t plus 0.5 d by dt x of t plus 0.4 x of t. Again, we have here y of t, y of t, y of t in the left half, and we have x of t, x of t, x of t in the right half. Now, converting the entire differential equation from time domain to Laplacian domain, I use a Laplacian transformation which directly says that differentiation in time domain is multiplication by s in frequency domain. So you have d by dt as s square y of s plus 0.6 s y of s plus 0.7 y of s equal to s square x of s plus 0.5 s x of s plus 0.4 x of s. Again, making y of s as coefficient free, making y of s as coefficient free, I divide the entire expression by s square. So we have y of s plus 0.6 s 0.6 y of s upon s plus 0.7 y of s upon s square x of s plus 0.5 x of s upon s plus 0.4 x of s upon s square. Then making y of s as common, left inside is 1 upon 0.6 upon s, 0.7 upon s square. Similarly, x of s is taken outside and we have 1 plus 0.5 upon s, 0.4 upon s square. Y upon x will give us 1 plus 0.5 upon s, 0.4 upon s square divided by 1 plus 0.6 upon s, 0.7 upon s square. So now I have equation number 2 in the ratio form as y upon x, followed by the coefficients of x and coefficient of y. Now I introduce a intermediate variable as w, wherein w by x into y by w. So I can say that w upon x is the 1 upon 0.6 upon s plus 0.7 upon s square, and similarly y upon w is basically 1 plus 0.5 upon s plus 0.4 upon s square divided by 1. So now we have two equations as equation number 3a as w upon x and equation 3b as y upon w, wherein 3a corresponds to 1 upon denominator and 3b is basically numerator upon 1. Now, equation 3a will be used to construct this graph, and similarly equation 3b can be used to construct the remaining part of the graph. So we can see here we have ws will be equal to minus of 0.6 upon s ws minus 0.7 upon s square ws and plus x of s. Fine. Same way we can have y of s equal to w of s plus 0.5 ws upon s plus 0.4 ws upon s square. So this is the simplification of equation 3a and simplification of equation 3b. And then we have came up with this final graph. So we came over here, W of S equal to minus of zero point 0.6 Ws upon S. So minus of zero point 0.6 will be the amplifier block, 1 upon S as the gain of the loop, and then you have Ws over here. Secondly, we have minus zero point 0.7 as an amplifier, 1 upon S as again the gain of that path. So we have here as 1 upon S into 1 upon S comes out to be 1 upon S square, and then finally this is the expression we are going to get for equation 3a. Coming to equation 3b, we have zero point 0.5 upon S, zero point 0.5 upon S, zero point 0.4 upon S square, zero point 0.4 upon S square. This is the final expression that we're going to get in the case of Y of S. This is our direct form to df2. I hope the things are pretty clear to you and you have understood the entire expression of the meaning of df1 and df2. Thank you all of you. Stay safe, and I hope please like the video, share with your friends, subscribe and comment what was the content and how you like the video. Thank you very much. Stay safe.